I just watch the video later.
We should really get it so we can live stream, so that you can watch the video as it's being filmed. And this is where we need Spaceballs with that, great advance. All right. So, leaving Spaceballs, which is a great movie, although it does connect to the Swart Space, which we will talk about eventually. I want to talk a little bit about some of the integrals we're going to be needing for development of probability theory. And this at least gives us a way to mix up. I know some of you have seen a lot of this probability stuff before. This way we can go back and do a little bit of complex analysis. So densities. So they're non-negative, integrate to 1. And then the area from A to B is the probability that your random variable takes on a value between A and B. So the most important for us is the normal. And we'll say X has a distribution with normal mean mu, variance sigma squared, if the density satisfies 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. Most of the time we'll look at normal mean 0 variance 1, the standard normal. You could pass from one to the other with just a change of variables. So we proved why this is the correct normalization constant. We did the polar trick by multiplying it by itself. We also talked about using this as a transform. If we can transform this to the gamma function, and then this is a special value of the gamma function, it's related to gamma of a half. The gamma function generalizes factorials, so we call gamma of s was the integral from 0 to infinity, e to the minus x, x to the s minus 1, dx. Gamma of n plus 1 is n factorial. Okay, so let's say x is normal, mean 0, variance 1. What we might want to do is we might want to calculate the Fourier transform. And so we're going to define the Fourier transform of a function to be the integral from minus infinity to infinity of f of x e to the negative 2 pi I xc dx. Dx, sorry. So we take x as an input, and we get a function of c as an output. Because a certain person is not here who is a double major with physics, I don't have to worry about physics notation. And I will just use this notation. There are 3 different notations you can use for the Fourier transform. They come from slightly different definitions in terms of where you have 2 pi's or square roots of 2 pi's. Depending on what you're doing, different ones are better. Always check your book, and if you're using a package like Mathematica, check to see how Mathematica normalizes things. Fortunately, if you're using the wrong normalization, you should be off by a factor of 2 pi or square root of 2 pi, and it should be pretty clear where the mistake is, or the normalization difference is. You always want good notation. We start off with the function f as input. We have a new function. We're putting a hat to denote the fact that it's the transform. Some people sometimes like to write maybe the Fourier transform of f evaluated at c. We are going to only be dealing with Fourier transforms of densities. So if f is a density, f is non-negative. So if we were to try to look at does this integral exist, well, if I just take the absolute value, it's less than or equal to the integral of the absolute value. And what's the absolute value of e to the negative 2 pi I xc? It's 1. So we'll be fine. So this will at least make sense for all real values of c. And then the question becomes, when will it make sense for complex values of c? It seems to be reasonable that if f has sufficiently rapid decay, this will make sense for some complex values of c as well, that it might exist for a strip of c. If you think of f of x as the normal, f of x is decaying like e to the negative x squared. So if I write c as a plus ib, the a is no problem. That's just a nice real number. The b would give the I, and the I becomes a minus 1. It reinforces with this, becomes a plus 1. We get an e to the 2 pi bc. And so depending on the sign of b, as c goes either to positive infinity or negative infinity, you have exponential growth. So you would need to have a little bit more than exponential decay in f for this to make sense. Or if f has exponential decay, it would make sense for certain values of b. So maybe f is decaying like e to the negative x over 5 in both directions. So maybe this is less than or equal to e to the negative absolute value of x over 5. Then this should be okay if maybe the absolute value of b is less than probably 5 over 2 pi. Oh, maybe, sorry, the 5 should probably be down below, sorry. 1 over 10 pi. Because then when I put that in here, the argument I have is going to be smaller than this, and I'll have a little bit of extra exponential decay. So a big issue is going to be for which functions are we able to deal with everything. A really nice set of functions is the Swart Space. And so this does actually link back to the Spaceballs reference at the beginning of the day. I wasn't going to go here, but with the advances of home video technology, we can actually get the lecture before it's given. How many of you have seen the Swart Space before? Okay, the Swart Space is basically the set of functions that have so much decay in every conceivable way you need to look at them that you don't have to worry about any convergence issues. So basically, f and all its derivatives decay faster than any polynomial as x goes to infinity. So that's a wonderful space of functions to look at. And the way we'll typically write it is 1 plus x squared to the nth power times the nth derivative of x will go to 0 as x goes to plus or minus infinity. So sometimes you put in the little 1 over here just because you want to be careful as to what's going on at 0. You don't want necessarily the bound, but we really care about what's going on at 0. If it's well behaved everywhere, then what's going on in a finite interval near the origin is no problem. Sometimes you might be concerned with how these decay constants depend on m and n. Not surprisingly, as you vary m and n, that should affect the rate of decay. But essentially, because these functions decay so rapidly, everything is going to be nice with them. So the first thing we might want to ask is, what is the Fourier transform of the standard normal? So what is the Fourier transform of the standard normal? So we want to integrate from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 e to the negative 2 pi I x c dx. Are there any values of c where we can do this integral? Any values of c? So there can't be that many candidates to try. What's the best candidate to try for c? 0. If we try c equals 0, then this just becomes 1, and this is just the integral of the Gaussian. So we can do at c equals 0. We get 1.
Real C?
So then the next question is, can we evaluate this for real c? Is it real c that would be the easiest to evaluate this at? I claim there's something easier than real c. In the interest of full disclosure, I haven't prepared today's lecture. I want to actually do these integrals cold. and talk about thought process as to how you would attack this. I can think of two ways to attack this. One way is, can you tell me a good value of C to study? So you said real C. I'm not doing cartwheels. I'm not excited about real C. So try something else. I'm sorry? Well, there's no reason to say negative I. We can if we want to, but it's not going to make much of a difference because the negatives will reinforce. But so you want to try an imaginary value. Why would it be good to try an imaginary value?
Decay rate is fast enough.
So first of all, if we put in C as imaginary, pure imaginary, we're going to have plenty of decay. We've got an e to the negative x squared. That's going to beat the crap out of some constant times x. But what's the advantage of putting in C being pure imaginary? Everything's real. This is just a real integral, and we just have to shift things. We can complete the square. So let's try C equals I times t. Okay, and so if we do that, we get the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 e to the, now the i's cancel, we'll have a positive here, we'll have a 2 pi I t, no, sorry, the i's are gone now, and we'll have this. And now you can begin to see what a pain it is to work with all the different factors of 2 pi. Right? Do we want to have a 2 pi t? What would we rather have? We'd probably rather have a t, or maybe 2t over 2. Oh, and I'm sorry, there should be an x here. Sorry. So we probably don't want the 2 pi. So maybe when we're choosing our value of c, do we want to divide by 2 pi? Or do we want to keep it like this? You can play these games. I'll keep our original choice, but you can see now why people have different notations and become passionate about it. We'll keep the one we have here. So what is this looking like over here? What do you think we should be doing? Oh, and what is d, and then dc becomes I dt, right? I'm sorry?
We're integrating with respect to x,
right? Oh, so we're integrating with respect to x. Oh, good, thank you. Sorry. Yeah, sorry, thank you. Sorry. Good. So what does this exponential look like over here? What should you be thinking? Complete the square. So we now get the integral from minus infinity to infinity, 1 over square root of 2 pi e to the negative, and we'll have x squared. Now, we want this over 2, and so since we want this over 2, we'll have to multiply, so we'll have a minus 4 pi xt. We'll divide by 2. Well, if we want to complete the square, we're going to have a 2 pi xt. So we should then add, I think we need a 2 pi t squared. And then we have to subtract a 2 pi t squared dx. And so we've just completed the square. And now when we cross multiply, we will get x minus 2 pi t squared. Now we'll have this part that will have to come out. Now we're going to have a minus, and a minus becomes a plus. So what comes out, we'll get an e to the 2 pi t squared over 2, integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x minus 2 pi t squared over 2 dx. What does that integral equal? I claim this is an easy integral to evaluate. It's got to be 1. Why is it 1? It's a shift. It's a Gaussian with mean 2 pi t and variance 1. We're just integrating a probability distribution. All right, so because of that, we now get the answer is just e, and I'm going to simplify things a little bit. So we'll have a 4 pi squared t squared over 2. So I'm going to write this as 2 pi squared t squared. I claim this is not the best way to write it. Any thoughts on how we should rewrite this? So we've calculated, we have the answer. But I claim that this is not the best way to write the answer.
2 pi t squared over 2.
Nope, not quite. What are we trying to do? What's the whole point of this? We're trying to calculate the Fourier transform of f. What's the function? What's the input? The input is supposed to be what? C. And now we have something in terms of t, but we have a relationship. C equals IT. So I want to write this in terms of c, because at the end of the day, the purpose of this is to calculate it as a function of c. Well, if c equals it, c squared is minus t squared. So this would become e to the negative 2 pi squared c squared. So we get the Fourier transform at c is equal to e to the negative 2 pi squared c squared if c equals it, where t is real. So we've calculated the Fourier transform, sadly, not at the values of c we want. We want c at the real values. We got c at the imaginary values. Is this good enough for us?
Since we know it converges everywhere, and it's holomorphic,
Yes.
we have it on a set of accumulates.
Excellent. It's our accumulation theorem. This is the power of complex analysis. We know if two functions agree on a set of points that accumulate, they must be the same. We care about this function when c is real. We calculated it when c is imaginary, and we have an answer. These two functions, phi hat of c and e to the negative 2 pi squared c squared, agree when c is pure imaginary. They agree on a set that accumulates. Is this function f hat of c defined for all values of c? Yes. So as f hat of c is holomorphic for all c in c, as f hat of c and e to the negative 2 pi squared c squared agree on a set that accumulates, they must be equal. Does this contradict any of our theorems? Because now we have a holomorphic function and it's not bounded. Is that okay? Yeah, this function is not constant. Is that okay? Because our initial function, this function is definitely bounded when c is, let's look at it this way. If I now replace c with a real value, we get something that's bounded. And we talked about how earlier, when we put in a real value, we have something that's bounded. So when c is real, we have a bounded function. This function is not constant. Shouldn't a bounded function be constant? Am I making a mistake? Okay, what's the mistake I'm making?
You're only considering the real axis.
Good, I'm only considering the real axis. Remember, we only have this wonderful theorem that a bounded function is constant if it's entire, if it's defined on the entire complex plane and is bounded there. It's perfectly okay for our function to be bounded on the real line, as long as it goes off to infinity someplace else. And in fact, we can see when we take c to be pure imaginary that this is actually growing greatly with the absolute value of t. So this is a really nice way to calculate the Fourier transform by using our accumulation theorem. I was originally going to show you a proof of trying to do this by doing like a contour integral and taking a giant rectangle and just shifting things. But I think this is a better proof. And it really emphasizes the idea of what is fundamentally different about complex analysis from real analysis. If we understand what's going on at a set of accumulation, then we know it everywhere. So all we have to do is show two things agree on a set that accumulates. We've actually done a lot more than we need to. This is more than just a set that accumulates. It's a set, solid, infinite line. It's just easier to do that than a sequence. Okay, so any questions about this? So we've now calculated the Fourier transform of the Gaussian. Now, this can show you a little bit of why there's such a fight over the correct normalization of things. So, does anybody know what a stable distribution means?
Is it when you add it to itself, or like convolve it with itself, you get the same distribution?
Yes, so a stable distribution is when you take independent copies and add them. The shape doesn't change. Now, not surprisingly, the mean could change, the variance could change, but the shape doesn't change. There are not that many stable distributions. The normal is a stable distribution. Sums of two normals is normal. It's a great calculation to do. Another distribution that is stable is the Cauchy. This was given to me years ago by an anonymous probability student. It's sadly been truncated, but it's a nice happy Cauchy distribution. Cauchy plus Cauchy is Cauchy. It's a wonderful calculation. The Cauchy is a stable distribution. Poisson is another stable distribution. Now this is stable with respect to addition. And the shape may change. That's going to happen typically. But if the shape doesn't change, that's really nice. Does this remind you of any concept you might have seen anywhere in mathematics? Where I have a process and maybe a value may change, but the fundamental shape does not change. Doesn't it kind of sound like eigenvalues, which are very useful? So let's make a meta principle. Rather than just looking at eigenvalues and eigenvectors or stable distributions, let's look at things whose shape is invariant under a process. Can you give me another distribution? Maybe it's one we've already seen that's invariant under some process that maybe we're looking at right now. If you look at the board, I claim there is a distribution that is invariant under a certain process. The normal distribution is invariant under the Fourier transform. It rescales it a little bit as to which normal distribution it is. There'll still be mean 0, but the variances will be changed. So here's an interesting question. Could I, instead of taking the normal distribution that has variance 1, is there a different variance that I could put in such that I would get exactly the same one out? So, root 2 pi. Maybe 1 over root 2 pi. So, I mean, if we want, all we would have to do is, we put a sigma squared here, put a sigma squared here. This is the advantage of being at the board, right? We can go through all this very quickly. Sigma squared here, sigma squared here, sigma squared here, sigma squared here. So we put a sigma squared here, what needs to come over here? Then we have to put a sigma squared up here. right? Because we're doing sigma squared over sigma squared. So I can put a sigma in there, a sigma in there. So put in a sigma over there, put in a sigma over there, put in a sigma over here. And then when we come all the way down to over here, we'll have a sigma squared, we'll have a sigma squared. And so now, if we want them to have the same shape, we would have e to the negative x squared over 2 sigma squared being compared to e to the negative 2 pi squared sigma squared c squared. So we would want 1 over 2 sigma squared to equal 2 pi squared sigma squared, if I'm doing things correctly. So this would be sigma to the 4th is 1 over 4 pi squared. So sigma squared is 1 over 2 pi. So sigma is 1 over square root of 2 pi. And so the advocates for the square root of 2 pi, they have a good compelling point. When they use that, then the distribution is very nice in terms of how things go. And so this could even be arguing maybe you want to adjust how you normalize this Fourier transform, because if you adjust the scaling in here, that is the same as playing this game. Fundamentally, it doesn't really make much of a difference. It's just conversion factors. But I want you to get into the habit of how to think about mathematics. As you're going to define things, how do you want to define things? What ideas do you want to use? What things are going to be useful? This is really a generalization of eigenvalues. Eigenvalues are very useful for solving systems of equations. It turns out you can use the Fourier transform to solve systems of differential equations. And so we may actually talk about how to use the Laplace transform to do calculations like that.
Do you think the Fourier transform somehow is like a sort of matrix operator?
You can think of these as matrix operators. The space that you're looking on, though, is going to be a difficult space to work with. But you have a nice operator, and you can always, the question you want to talk about is diagonalizing the operator. And what does it mean to be an eigenfunction of an operator? So I mean, there's great mathematics lurking in the background. Okay, any questions about this calculation? So this is at least a legitimate complex analysis part of the course. We've at least done complex analysis today, and not just probability. And again, the accumulation theorem is really what's lurking in the background. All right, so any Dickens fans here? No Charles Dickens fans? This is a liberal arts college. All right, which of Charles Dickens' works is clearly an example of being paid by the word? A Tale of Two Cities, exactly. It was the best of times, it was the worst of times. It was the age, you can tell this is being serialized and he's being paid by the word, okay? This is going to be A Tale of Two Densities. And I'll try to be more concise than Mr. Dickens. The best thing he ever wrote, though, was the claim that Hill House Avenue at Yale is the most beautiful street in America. Okay, Tale of Two Densities. Let's let f1 of x be 1 over square root of 2 pi x squared e to the negative log of x squared over 2, and f2 of x be f1 of x times 1 plus the sine of 2 pi log of x. So I claim that these are densities. So we have to check two conditions. What are the two things we need to check? Non-negative and integrates 1. Do we agree that the first is non-negative? What about the second? Sine is always between -1 and 1. Okay. Do we agree that these densities are not equal? Yes. Sine of 2 pi log x is not identically. What values of x's are these defined for? Yeah, positive x. If you want, we can allow it to be x equals 0 and have it undefined there, but definitely not for negative values of x. So when you see two densities, or when you see any density, what's the first thing you should, we'll assume that they integrate to 1. We leave that as an exercise. Or maybe we'll have that pop out of things we do later. What's the first thing you want to know about a density? If you could know one piece of information about it. The mean. I was about to say as a hint, imagine you're a pre-med student in a calculus class. Yeah. First thing you want to know is the mean of the class. What's the second bit of information you want? Standard deviation, how spread out it is. And then if you allowed more information, you would keep asking for more and more moments. And we talked about moments last time, that the moments hopefully will allow us to figure out which distribution we have. That a sequence of moments uniquely specify a probability distribution. Unfortunately, the reason we motivated studying moments was through Taylor series. And there's a huge problem with Taylor series. We have the function e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. And if we look at this function, all derivatives vanish at x equals 0. Functions like this is why real analysis is hard. We do not want something like this to exist. We would love a function to be uniquely specified by its Taylor series. If I give you a Taylor series that's identically 0, what function should I be specifying? More than constant, because I'm telling you the Taylor series is identically 0. Which constant? 0. If I give you a function, all of whose derivatives, including the value of the function at 0, are 0, I should be thinking about the 0 function. I don't mean to belittle what students are protesting across the country, but this is something we should really be protesting. The fact that we can have a function, all of whose values, all of whose derivatives, everything at the origin is 0, and the function is not identically 0. This is terrible for us. If we plot what's going on, it has such rapid decay at the origin. It's indistinguishable from flatness. Things like this should not be allowed to exist, but they do. And this is why real analysis is hard. This is why complex analysis is much nicer. Complex analysis will not allow you to consider functions like this as infinitely differentiable. Now, if a function's differentiable once, what do you know about it in complex? Infinitely differentiable, and what else? So if a function is complex differentiable once, it's infinitely differentiable and nope, and it's analytic. It equals its Taylor series expansion. This function does not equal its Taylor series expansion as a real analytic function. Therefore, what can you conclude about the complex differentiability of this function? It's not complex differentiable. If it was complex differentiable, then when we just specialize to x being real, it would have to be given by its Taylor series expansion. So this function cannot be complex differentiable, even though it's infinitely real differentiable. Anybody see what goes wrong? Of course, we'll look at the function e to the negative 1 over z squared if z does not equal 0, and 0 if z equals 0. So something must go wrong with this function. So it's not complex differentiable. What's the problem?
Approach along the 1 plus I line.
The what line?
The 1 plus I, 2 times 1 plus I. Then our exponent will be imaginary.
I would just go just along the imaginary line Just take z equals it.
Okay, yeah.
Because if you take z equals it, then you get I squared is -1. You get e to the 1 over t squared, which goes to infinity as t goes to 0. So this function is not even continuous. We shouldn't be discussing whether or not this function is differentiable. It's not even continuous. This really shows you how good of a job complex analysis does as gatekeepers. It will not let functions like this into the mix. Now, I'm talking about how difficult real analysis is, how difficult probability is. There must be some reason I've written down these two functions. Anybody want to hazard a guess about what these functions have in common? What would you guess?
Moments.
Probably have the same moments, but they're different. So they have, same integer moments. So in order to tackle both functions at the same time, I'm going to define a new function. F of x is equal to 1 over square root of 2 pi x squared e to the negative log of x squared over 2, 1 plus c times the sine of 2 pi log of x. And what will be the choices of c we'll want to study? So this allows me to attack both of these densities at the same time. What should my values of c be? 0 and 1. So really, if I can do this, if I can calculate the moments of this one, I then just specify c to be 0 or 1, and I get both of them immediately. And just saves a little bit of time. OK. So we've got about 10 minutes left. Let's see if we can actually calculate their moments. Now, again, looking in the background is we eventually are going to want to use our accumulation theorem to prove the central limit theorem. That for two distributions, if they agree on a sequence of moments that accumulate, they must be the same. So for these functions, even though they will agree at integer moments, there must not be a sequence of moments that accumulate where they agree. And in fact, they'll only agree, I believe, at half integral real moments. Okay? So let's calculate moments. So we want to calculate the expected value of x to the a plus ib. We're going to calculate a complex moment. This is going to be the integral from 0 to infinity of x to the a plus ib, 1 over square root of 2 pi x squared. We'll have e to the negative log of x squared over 2, 1 plus c sine of 2 pi log of x dx. Okay. So this should be screaming change variables. What is the change of variables we want to do? When you look at this. Any thoughts on what variable we should change? If you want to ignore the c part over here and just look at this part over here. So we have a 1 over square root of 2 pi x squared e to the negative log of x squared over 2. Which part really scares you? Which is something you've never seen before? The log. So what kind of change of variable should we try? Yeah. I'm going to use t equals log of x, and then dt becomes 1 over x dx, or if you want, dx over square root of x squared. And you can see the 1 over square root of x squared is hinting that you might want to change variables by t equals log of x, because that's going to make things very nice. Now, if x goes from 0 to infinity, t is going to go from minus infinity to infinity. So this is going to go the integral from minus infinity to infinity. Now x, we've got to figure out, if t is equal to log of x, then x is equal to e to the t. Yes? So we get e to the t a plus ib 1 over square root of 2 pi e to the negative t squared over 2 1 plus c sine of 2 pi t dt. What does this look like? And if you want, forget about this part over here. What does this look like so far? Same thing we were just doing. Right? Here's the normal density. I believe the name of the density we're looking at is the log normal density. Not a surprising name. And it looks like we're calculating something related to a Fourier transform. Modulo how we choose things with our 2 pi's and all that stuff. Right? We can always fix that by putting in a minus 2 pi I and divide by 2 pi I. We do have this sine of 2 pi t, though, which looks a little bit annoying. Is there any way to view that in a good manner? How should we view sine of 2 pi t? We can write it as an exponent. So this is going to be the integral from minus infinity to infinity of e to the, I'll write it as negative 2 pi a plus ib t over, well, I'll write it like this. Minus a minus ib over, let me do it slowly, minus 2 pi, and I want a 2 pi down below, negative a minus ib times t. Because this is looking now like the Fourier transform, which we just calculated earlier at the value negative a minus ib over 2. Right? Now we have 1 over square root of 2 pi e to the negative t squared over 2, 1 plus c. Now the joy. We write sine as e to the I theta minus e to the minus I theta over 2. So we use sine of theta is e to the I theta minus e to the minus I theta all over 2i. And us theta is going to be 2 pi t. Okay. And so now when I do this change of variable, we will get e to the 2 pi t I minus e to the negative 2 pi t I divided by 2i dt. We now have 3 terms. The first term is just going to be the Fourier transform So, this is, let's say this is the standard normal density. The first term is just the standard normal density evaluated at the point negative a minus ib over 2 pi. Everybody agree with that? And we know what that is because we just calculated that a moment ago. The next piece, it's going to be c. We still have the standard normal density, but now instead of having this, we have a 2i down below. Okay, we can divide by 2i, not a big deal. And we have an e to the 2 pi ti. So when we put that in here, we're going to be shifting things a little bit. Right? And so the effect of this is to just shift this exponent in the imaginary part. How much are we changing b by? Let's see. We've got 2 pi divided by 2 pi, so we need a 2 pi down below. So I think what we need to do is multiply by 2 pi over 2 pi, so we get a 4 pi squared t over 2 pi. And then we have the 2 pi here. We have a minus and a minus. One of them is going to have a minus sign, one of them is going to have a plus sign. Unfortunately, it does matter which one because we have a minus sign here. But when you figure out what the algebra is, we're going to have a minus a as before, minus ib, and then I think it's going to be minus I 4 pi squared over 2 pi. I might have made a small algebra mistake, I don't care. I really just care about the general idea that we can actually do these calculations. The next one is going to be very similar. It'll be minus c over 2i, and then it'll be f hat of negative a minus ib, but now it'll be plus an I times 4 pi squared over 2 pi. And that's the answer. I think the other class might be leaving a little bit early. Yes, the other class is leaving early. All right, we still have a little bit of time. We know what f hat is. We can calculate all the moments. Okay? So as a nice exercise, finish the calculation. I'm not going to assign this to you as a homework problem. I strongly encourage you to do it to finish the calculation. But at this point, it's just algebra. It's just substituting in. And I think what you'll find is that as long as a is a half integer real number and b is 0, the moments agree. But those are the only times the moments agree, when you just slug through all the algebra. And so we have 2 distributions that have the same integral moments. They even have the same half integral moments, but they do not agree in any place that accumulates. So again, it's a really good exercise to just finish the calculation. Almost surely there's an algebra mistake here. I do not promise that the algebra will be correct, but the algebra doesn't really, okay, the algebra matters, but it's not the big thing. The big thing is how you attack a problem like this. There's a lot of great things here. Is this sign, it's not a random thing that they put in here. The reason we have the sign is related to an exponential. We have an exponential change of variables going on. And what that means is this just basically shifts the Fourier transform. And that's why things become so nice. We might expect some amounts of cancellation from these things. We can then put in c equals 0, c equals 1, and see what's going on. So this is complex analysis now coming into probability and showing us why we have trouble. Just because these 2 densities agree on half integral real moments, that's not going to be enough. We don't have something that accumulates. And this is why we have to be so careful in proving the central limit down. All right, so this is probably a good place to stop.